Welcome back, Oxnard College Physics. Justin Miller here. We're going to continue looking at resistive forces with the resistive force being proportional to objects of velocity. What we want to look at is another case in which a resistive force acts, but a case in which we're going to say that constitutes the net force acting. So, what if an object has some initial speed or initial velocity and is subject to only a resistive force. R hat is equal to negative B V hat. Question mark on there. Well, in this particular case, it wouldn't be dropping some object from rest within some fluid. It'd be some object that's already moving through some fluid or through air in a direction in which gravity is not affecting its motion. So you could have something maybe sliding across a frictionless surface that's encountering this resistive force. That would be a decent model, but ultimately we just want to see what happens in this case. So we've got ourselves the net force is equal to, in this case, negative B V hat, and as we always have, the net force produces the acceleration of the mass. Thus, we have that A hat is equal to negative B V hat, which furthermore gives us that A hat is then equal to negative B over M V hat. So there's the correlation with the acceleration and the object's velocity. What we want to do, once again, is figure out some time correspondence to the object's velocity itself. So we can take this. By definition of acceleration, we can write ourselves that dv hat by dt is then equal to negative b over m times v hat. So here's the acceleration, and here is the resistive force itself divided by the mass, responsible for the overall acceleration. So let's just go ahead and see if we can solve this one out. We get another differential equation. This one's a lot simpler to solve, super directly integrable. So let's just go ahead and take a look at this and separate this out. So I divide both sides by v hat, and I'll move the dt to the other side, and we can write this as dv hat over v hat is equal to, we've got negative b over m times dt. Not necessary to have the hats anymore. We're just looking at the speed of the object now. And we can write this then as the integral of dv over v from some v initial to some v final is equal to negative b over m dt. Take the integral of that. Do to one side, do the other. Now in terms of the time, there is a time initial that correlates with the initial velocity and a final time which correlates with the final velocity. So I'm not going to put in those limits of integration as they aren't necessary because they're tied with these limits here. So let's just go ahead and see what we get out of this. We've got the integral of dv over v. That's just going to be the ln of v. Evaluated from v final to v initial will give us then ln of v final minus the ln of v initial is equal to negative b over m times a t. Great. We've got ourselves a nice relation here. We can sum this up a little bit more. I can join those two ln's together and write this as the ln of v final divided by v initial is equal to negative b over m times t. And what do we want to get? We want to get what v final is in terms of everything else. So we can take the exponential of both sides and get ourselves that v final divided by v initial is equal to e to the negative bt over n. Solve this out for v final. V final is then equal to v initial times e to the negative bt over m. This is v of t. Depends on the initial velocity of the object and then we have the exponential decay of the object's speed with respect to time. It depends on the mass of the object and the coefficient of proportionality regarding the resistive force itself. So in the end, we can write V of t is equal to V initial e to the negative b t over n. So that's what we end up getting when we have just the resistive force acting on the object. It's kind of a simplified version of what we looked at prior to this. Nice. Lastly, we want to look at one more model in which an object is moving through air at a decently high rate. This is generally reserved for things like airplanes, baseballs that are thrown at high velocities, skydivers, things of that nature moving through air. And for those particular cases, the resistive force actually goes as the velocity squared. So we'll put for object traveling at a high speed through air, the resistive force is given by R hat is equal to negative 1/2 rho A d V squared. Let me get rid of this. I'll just say magnitude, so we don't run into vector peculiarities here. So the magnitude of the resistive force is given by 1/2 rho A dV squared, and is always directed opposite the motion of the object. All right, so what do we want to know? We want to know what some of these quantities are. Rho is the density of air. Under normal atmospheric conditions at 20 degrees Celsius, rho is approximately 1.20 kilograms per meter cubed. We've got ourselves A, that is the area of cross-section of the object. Which is facing perpendicular to the direction of motion. So we'll say the area of cross-section perpendicular to the object's motion. And we've got ourselves D. D is known as the drag coefficient. Determined by properties of the object itself. Ultimately, aerodynamic properties of the object substantiate the object's drag coefficient. And then V, the object's speed. What do we have? It goes as the speed squared. So the faster the object's moving, the much greater the resistive force is relative to when it's moving slower. So that's directly proportional to the velocity. So let's look what we can do of this. what we can't or what we won't, go from there. Consider an object you know what, let's not do drop this. Consider an object under the action of this resistive force and gravity as falls down. So, much like we had in the previous case, we've got ourselves the force due to gravity acting on some mass, and we'll have some resistive force. What can we do with this? Again, we can look at the net force being equal to the resistive force plus the force due to gravity, which then can be written as, I'm going to write this as negative 1/2 rho A d v squared plus mg. So in this particular incorporation, I really just need to have that the direction of the resistive force is opposite the direction of the gravitational force. So I got rid of the vector hats and negatives up, positives down. Maybe a little confusing, but it's really irrelevant. We just need opposition between these two quantities here, directionally. So that's in there. And what do we have? Well, overall, this produces the overall acceleration of the mass. M-A hat. All right. So then, when we go ahead and start looking at this, we run into some problems because we can write this all out and say that A then is equal to negative 1/2m A d v squared plus g. That would be okay. And then we go ahead and say, well, A is the same as dv by dt, which is then negative 1/2m A d v squared plus g. So we get another differential equation that looks similar to what we had before, but there's one important factor here, and that is that the velocity is squared in this particular case. So now we're trying to find a function that we can take one derivative of that function, we get back some constants, and we get back that function squared. That ends up being not the easiest thing to solve out. This definitely is not directly integrable. You need some higher level mathematics, some expansions, and stuff like that. We're not going to worry about the true solution for this at all. All that we're really going to be concerned with is, well, what's like the terminal speed. So we'll just put up here, difficult to solve. Let us just find the object's terminal speed. In this case. How can we do that? We go back to the acceleration. We still note that the terminal speed occurs when the acceleration drops down to 0. So, let us go ahead and roll with that. The object will obtain terminal speed when the acceleration drops to 0. Let's say goes to 0. So from this top, A is equal to negative 1/2 quantity m adv squared plus g. We've got ourselves that 0 is equal then to negative 1 over 2 m a d v squared plus g. And we'll go ahead and subscript this with the little v sub t because now that represents the terminal speed of the object. I'm going to solve this out for v. We can subtract g from both sides. Notice that it'll cancel out a negative sign over there. Multiply by 2m, then divide by ad, forgetting the rho there. Took it out of that too. Rho, messy. Rho. We can solve this out once again and get ourselves 2mg over rho ad is equal to v sub t squared. And then solve this out completely for v sub t. Terminal speed is then equal to just the square root of 2mg divided by rho ad. That's it. Depends on the mass of the object, the drag coefficient, cross-sectional area, and the density of air. That's all that we're really going to do with this. So mostly I focus on the case where the resistive force is proportional to the velocity. This is still part of it, and that's it. All right.